Hello. So in this seminar, I'll be presenting our work on cross-sensor domain adaptation for 3D object detection using stationary object aggregation pseudo-labelling, a method which we call SOAP. And this presentation and this work is part of the publication in the Winter Conference of Application of Computer Vision 2024. So in this seminar, I'll first go over some background information on LiDAR, 3D object detection, and the tasks that we're interested in, the domain adaptation task, and introduce our method SOAP, and then introduce some experiments and results to show the effectiveness of our method, and then discuss some limitations. So LiDAR stands for light detection and ranging. It's an active sensor that works by measuring the range by emitting a laser beam directly at the target and detecting the reflected beam and then calculating the range based on the signal delay. Compared to camera sensor and radar sensor, a LiDAR can directly produce really accurate range measurements and can operate in low light conditions as opposed to camera sensors. And as a result, it's very favorable and widely adopted in the autonomous driving applications. A LiDAR sensor is going to produce 3D point clouds representing the surrounding environments, like the example shown here. Typically for autonomous driving application, it has a max range ranging from 75 to 200 meters, but it has a very low vertical resolutions, ranging from 32 to 128 beams. And as a result, you're going to see some scan line patterns on the ground from a LiDAR scan, 360-degree LiDAR scan from the autonomous driving vehicles. And to further demonstrate this scan line pattern that are distinct to each LiDAR sensor depending on the beam patterns, here are two examples of simulated LiDAR point clouds of the same scene using two different LiDAR sensor configurations. And as you can see, even scanning in exactly the same environment, the LiDAR can produce vastly different scanline patterns and different point cloud distributions. Now, using those LiDAR point cloud scans, our work is interested in the problem of 3D object detection, which involves identifying and locating objects in the 3D environments, including object classification, identifying the location, the dimensions, and the heading of the objects. Now, because of the aforementioned problem with the different scanline patterns and different point cloud distributions resulted from different LiDAR sensors, this 3D object detection is going to have different performance when applying to a different sensor compared to its training distribution. And this is the problem of domain adaptation that we're interested in. In particular, the domain adaptation aims at improving an object detection's performance on a particular target domain using the labeled source domain and in some cases the unlabeled or partially labeled target domain. So in other words, during the training time, our object detector will be trained on the source domain training data and in some cases partially labeled target domain data. But our goal is to improve the performance of said object detector on a target domain that's collected using a different sensor. And there are two different variants depending on if the target domain labels are used. For unsupervised DA, we assume a unlabeled target domain, and for semi-supervised DA, we assume a partially labeled target domain. So a small amount of target domain data is labeled. And several existing work on domain adaptation involves using what's called a pseudo-labeling technique, which basically means after training an object detector on the source domain, we'll feed it the target domain input data to target domain point clouds, and we'll treat whatever prediction coming from this object detector as a ground truth label, but it's not actually ground truth, so hence we call that pseudo-labels. And the pseudo-labels can then be treated as ground truth to fine-tune or refine another model on the target domain. And several works aim at improving the pseudo-label quality, such as streaming or ST3D, which involves some post-processing technique, such as filtering, smoothing the trajectory, interpolation, extrapolation. And for ST3D, some certain voting and memory mechanism can be introduced to improve the consistency of the pseudo-labels. Another line of research involves developing training technique to improve the performance after when we utilize the pseudo-labels during training. Some state-of-the-art includes ST3D and SSTA3D. Now, our work is kind of parallel and complement the existing works. And the main motivation for our method SOAP is that we noticed that the distinct scanline patterns is the cause of the domain gap, the performance drop when we move to a different sensor. As can be demonstrated in the example here, where we have sparse point cloud, sparse object from two different data sets. Now you can see that the vertical point cloud distribution as shown in the CDF here is very different for the different data sets that are collected using different sensors. However, interestingly, after we combine and aggregate multiple point clouds, this problem, this distinct scanline pattern, can be alleviated. And as shown both in the visualization and in the CDF plot, we don't really see that distinct vertical point cloud distribution. Rather, we see a very smooth distribution of the point cloud's z values. And quantitatively, in our preliminary experiments, we found that just introducing a few more frames as input can reduce the domain gap compared to just using a single frame point cloud. Further validating our point of aggregating multiple point clouds can help with domain adaptation. So the core idea of SOAP is to take this aggregation idea to the extreme by aggregating and combining the entire scene, the entire full sequence, which we call scene level full sequence aggregation. It is also the first step for our SOAP pipeline. It aims at reducing the aforementioned difference in the scanline patterns, specifically for stationary objects. So suppose we have some point clouds collected at certain timestamp tau and associated with a ego pose. So the ego pose represents the transformation from the ego vehicle's coordinate system to some arbitrary global and canonical coordinate system. So given those information, we can perform a transformation from each point cloud's local coordinate to a global coordinate by just applying this ego pose transformation. And we can apply that to another point cloud, let's say tau prime. And what this transformation will do is for static features, such as the corner of this building, in the global frame, they will be aligned to each other. And we can do this for every single point cloud in the entire sequence by just concatenating the transformed point clouds from each time step. And we will get a very dense point cloud, as shown in the example here. Now, in this kind of full scene or full sequence and scene level aggregated point clouds, the stationary objects, such as the vehicle parked on the side of the road, is going to be densified with a very more complete geometry. However, for dynamic objects, because we didn't account for the motion of those objects, the point clouds are going to be distorted. As a result, in the subsequent pseudo-labeling generation process, we cannot really train and generate pseudo-labels for those dynamic objects because their location can be anywhere along their trajectory. So instead, we train a model to generate pseudo-labels specifically for the stationary objects by taking advantage of the properties of the full sequence aggregated point clouds. To naively do this, we can simply filter the objects based on the speed or their displacements over time during training. But we observe that certain objects can appear stationary with very little distortion in their point clouds. And we call those objects quasi-stationary objects. And those objects can exist because in their trajectory, when they're near stationary, the eagle vehicle collected many points from those objects. So we have many observations when the vehicle is near, or when the object is near stationary, but we have very few points when the object is actually moving, resulting in a very stationary looking point cloud while the object is technically not stationary. And this causes problem with the training labels because certain objects like this will not be labeled as stationary objects for us to predict, but some other actually stationary object that looks very similar to this will have some positive labels. So then during training, the labels can be very inconsistent because of this. So instead of using this naive method, we propose a quasi-stationary training technique where we first identify the quasi-stationary objects, like the case that I show in the previous slide, using a quasi-stationary score. So this score represents how likely the object, the point cloud is going to be distorted at a certain location. And this is defined as a pairwise IOU weighted by the number of points to take into account the observation at each location. So back to the previous example, where the object here is mostly stationary, will have a very high QSS score. And hence, during training, we'll use this location and this bounding box as the ground truth, despite the fact that this object is technically not stationary. Whereas for the actually dynamic part of the object, where we see distortion and very few points, it will have a very low QSS score because the IOU is low and we have very few points. So it's down-weighted significantly. So using this QSS score, we can then filter the dynamic objects and identify certain dynamic objects that can appear undistorted by having a simple threshold. And this is how we generate pseudo-labels for those stationary and quasi-stationary objects. And after this, we can refine those pseudo-labels by what we call a spatial consistency post-processing, SCP technique. And this pipeline exploits the stationarity of the detected objects because we're trying to detect stationary objects, and therefore they should be consistent over multiple frames, and their location should be consistent in the global frame or global coordinate system, and the dimension of the bounding box should stay the same over time, assuming that we're talking about rigid objects such as vehicles. So to do that, we first transform all the detections from the previous step, the stationary pseudo-labels, into a certain global frame. We then perform a clustering operation of those pseudo-labels in the global frame to filter out clusters with very few detections. So a cluster with very few detections would be an indication of inconsistent detection over time. So we want to keep only the consistent ones. And then for each cluster, because the object size and object location should be consistent in the global frame over time, we combine all the boxes within each cluster using a weighted box fusion, which will weight the boxes based on the confidence from the previous step, and then producing one box per cluster representing that object. And finally, we'll transform all the boxes back to the local frame to obtain the pseudo-labels for each individual frame. And because the entire process shown here, the lower process is concerned with stationary objects, we don't really have detections for dynamic objects. And therefore, we introduce another pipeline where we use a standard pseudo-labeling technique to generate pseudo-labels and then combine with our stationary pseudo-labels to cover both the stationary objects and the dynamic objects. Again, the combination is using the weighted box fusion, which takes into account the confidence coming from each pipeline. And the final pseudo-labels can then be used to train another detector on the target domain, or be combined with existing approaches such as ST3D and SSDA3D. So that concludes our the pipeline for our method SOAP. And next I'll talk about some experiments and results. So to evaluate our method, we consider two state-of-the-art architectures, Centerpoint and VoxelNext, and two datasets, NewScenes and Waymo. They're collected using different LiDAR sensors. For NewScenes, it's the Velodyne HDL32E, and for Waymo, they're using their own proprietary 64-beam LiDAR. And the point clouds, as we seen in one of the previous slides, can look very different. For comparison, we consider a simple baseline of directly evaluating a source domain model on the target domain, which we call direct. For semi-supervised setting, we have a co-training baseline where the model is trained on both the source and the partially labeled target domain. The oracle in our context means that the in-domain performance, assuming a fully labeled target domain. So the model is trained entirely on the target domain. This will help us judge how much of the domain gap is closed by each of the method, including ours. For state-of-the-art methods, we compare with the aforementioned ST3D and SSDA3D for both unsupervised and semi-supervised settings. And of course, the SOAP represents the pseudo-labels produced by our method. And we also evaluate combining the state-of-the-art method with our method by using the pseudo-labels of our method, but the training technique proposed by each of those state-of-the-art methods. So first, we observe that the overall performance of SOAP pseudo-label improve over baseline by a significant margin. So compared to direct in both architectures, our pseudo-labels can close over 50% of the domain gap in the unsupervised setting. And in the semi-supervised setting, where 1% of the data in the target domain is available, we can close over 85% of the domain gap. And furthermore, this improvement of the pseudo-label is more noticeable for far-away objects, where the point clouds are significantly sparser than closer objects, and hence the effect of the distinct scanline pattern and distinct point cloud distribution is more detrimental to the domain adaptation problem. And we see that so because we're using full sequence aggregation to eliminate those scanline patterns and to densify the point clouds, we see a much larger improvement for those objects, especially for 30 to 50 meters. This can also be seen qualitatively in the two examples shown here, where for faraway objects, especially the ones that are parked on the side of the road, the SOAP pseudo-labels can very consistently detect those cases. And when we apply the SOAP pseudo-labels and combine that with existing techniques such as ST3D and SSDA3D, we find that in both cases, SOAP can improve those state-of-the-art method, showing that we are complementary to the state-of-the-art methods. In the unsupervised domain adaptation case, with the SOAP pseudo-labels ST3D using either architecture can result in a much larger improvement compared to the original baseline. And similar effect can be seen in the SSDA3D in the semi-supervised domain adaptation setting, where using the SOAP pseudo-labels together with SSDA3D's training technique, we can close over 86% of the domain gap, approaching the oracle performance, using only 1% of the target domain label. And finally, our ablation studies suggest that all of the proposed technique in our pipeline are effective at the domain adaptation, at closing the domain gap. And in particular, the quasi-stationary training and the stationary consistency post-processing pipeline both introduce large improvements for overall performance and for the stationary object performance. So there are several limitations to SOAP. First and most obviously, because we heavily utilize aggregation, we require the point clouds to be collected sequentially, and we require that we have access to the equal pose information. However, this is typically the case in the autonomous driving application, where the data is always collected continuously. And for equal pose information, that information can be obtained offline via methods like SLAM. And the second limitation is that our method assumes that the ego vehicle is moving relative to the environment. So our method will not be applicable to something like a roadside LiDAR, where the LiDAR sensor is stationary. And finally, we assume a sufficient number of stationary objects in the environment and for a particular class. So for environments where we have a lot of dynamic objects, or for certain classes where the objects are typically always moving, such as pedestrian or cyclist, our method cannot be as effective compared to the stationary objects such as vehicle and cars. And that concludes the seminar presentation for this work.